Hi, and welcome to this next topic on OCR A Level Chemistry. This is topic 17, and it's all about the alcohols. Now this, like the other topics in this organic chemistry section, have lots of links to other topics that I've done before, for instance, the bonding and structure one. I'm going to just quickly go over those things. If you need any more details on them, then just go to those videos. So alcohols, as we've said before, have an OH group. That OH group means that they can do hydrogen bonding with each other, so other molecules of alcohol, but also with water. So alcohols tend to be very soluble in water, and they have relatively high melting and boiling points because of those strong hydrogen bonds between them. They also have a relatively low volatility compared to, for instance, the alkanes. Volatility, if you don't know, is the tendency of a liquid to turn into a gas, and because of their strong bonds, they tend to have a low tendency to turn into a gas, compared to alkanes, which will turn into a gas relatively easily. The next part of the specification is about a classification of alcohols into primary, secondary, and tertiary. So here are three examples of alcohols. It's ethanol, this is propan-2-ol, and this one is 2-methyl-propan-2-ol. You see ethanol, the carbon, which is bonded to the oxygen, is also bonded to one other carbon. That makes it primary. In propan-2-ol, the carbon bonded to the oxygen is bonded to two other carbons. That makes it secondary. And in 2-methyl-propan-2-ol, the carbon bonded to the oxygen is also bonded to three other carbons, and that makes it tertiary. And the same with other organic compounds, you need to be able to do the combustion reactions for those. It says specifically for alcohols you need to be able to do a combustion reaction, and I assume that's because of the oxygen, which is already in the alcohol molecule, and that sometimes trips people up with combustion reactions. So I'll show you how to do one, the combustion of, say, propan-2-ol. So, same as we did before, still reacting with oxygen, still going to make only carbon dioxide and water as products. You just need to be able to balance it. So there's three carbons, so I make three carbon dioxides. There are 8 hydrogens in total on the left-hand side, so I need 4 water molecules on the right-hand side. And finally, we need to deal with the oxygens, so there are 6 in the 3 carbon dioxides, another 4 in the water, which makes 10. There's already 1 in the alcohol, so I only need 9 more oxygen atoms on this side, which means 9/2 oxygens. Same with the other ones, you can double everything, or you can write this as 4.5. Either way is fine. Now the rest of this video is all about organic reactions of alcohols, and changing those alcohols into other functional groups. So we've seen some organic reactions before, the addition reactions of alkenes and the free radical substitution for alkanes to make haloalkanes. There are 3 more for alcohols. One of them is oxidation, one of them is elimination, and then substitution with a halogen. Now, in organic chemistry, oxidation can have 2 meanings. Firstly, it could be the addition of an oxygen atom to a molecule, or it could be the removal of 2 hydrogen atoms from a molecule. And to oxidize an alcohol, you need what's called an oxidizing agent. An oxidizing agent is something which oxidizes another chemical, and as such it is itself reduced. And the oxidizing agent that you use to oxidize alcohols is called acidified potassium dichromate. And that acidified potassium dichromate is often written just as an O in square brackets to make things simpler. The O in square brackets just represents an oxidizing agent. So all of these 3 represent adding an oxidizing agent. So acidified potassium dichromate, if you want to write it out in words, acid and potassium dichromate, if you want to write it out as symbols, and then just an O in square brackets if you're going to put it into an equation. If you calculate the oxidation number of chromium in this, it's +6, so that's why it's such a good oxidizing agent, because that 6 can easily be reduced. And when this acidified potassium dichromate is reduced, it creates green chromium 3+. This compound is orange, and so when it is being used, it changes from orange to green, so you can see that colour change when the oxidation happens. Now with any oxidation reaction of alcohols, the first step is always to remove 2 hydrogens from that alcohol. One of those hydrogens has to be from the OH, otherwise it would be an alcohol reaction. And the second hydrogen comes from the carbon, which is next to the OH. So this carbon here directly bonded to the O, the other hydrogen comes from that carbon. So in this case, this hydrogen and this hydrogen get taken off to go with the oxidizing agent, which we represent as just an O, so that would be H2O. 2 hydrogens and then the oxidizing agent. And when you do that, you're left with a double bond between the carbon and the oxygen. Call that a carbonyl group. And you can see that that would be absolutely fine with secondary alcohols. You've got this hydrogen and this hydrogen. And it'd be fine with primary alcohols. You can take that hydrogen and either of those two on the adjacent carbon. But with tertiary alcohols, you've got this hydrogen, but there's no hydrogen attached to that carbon directly bonded to the alcohol group. So tertiary alcohols can't be oxidized. If you add acidified potassium dichromate, nothing happens. But we can show what happens to a primary and a secondary alcohol. So both of them just going to take off those two hydrogens to react with the O of the oxidizing agent to make water, and I'm left with a carbon-oxygen double bond, and the same for this secondary alcohol. Okay, now be careful with these because sometimes they ask for organic products of reactions, and sometimes they just ask for products of reactions. If they ask for the products, you have to include water. If you don't get that mark. So just ask you to draw the organic product, then these carbonyl compounds are absolutely fine. This one, because the carbon-oxygen double bond is on the end carbon, is an aldehyde. It's ethanal. This one, because the carbon-oxygen double bond is on the middle carbon, it's a ketone and is propanone. And for ketones, that's where it all stops. But aldehydes, they can be oxidized further. So for aldehydes, you can put twice as much oxidizing agent in. The first one does exactly the same as I just said. It removes two hydrogens in that reaction that we've just drawn, and the second oxygen gets added in between the carbon and the hydrogen to make a carboxylic acid. So I have changed this slightly just to show you. I've put two oxidizing agents in because you need twice as much, one to remove the H's, the second one to add oxygen. First one removes the H's, so you're left with an aldehyde or ethanal and water, and there's still one oxidizing agent left. That oxidizing agent gets added, so the O goes between the C and the H to make a carboxylic acid. This water is not produced now, it was produced in the first of the two reactions. And that's basically it. You just need to know the experimental conditions. And the experimental conditions for this, well, obviously they need acidified potassium dichromate as the oxidizing agent, and they also need to be heated. But when you heat a liquid, it tends to vaporize. So to stop all the products and the reactants from leaving the reaction vessel, what you do is you put on top of the reaction vessel a condenser, and that condenser, as the vapors go up into it, will condense them back into a liquid so they drop back down into the reaction vessel. What that's called when you place a vertical condenser above the reaction vessel is reflux. That's what that process is called. And so if you reflux a primary or a secondary alcohol with acidified potassium dichromate, you make a carboxylic acid or a ketone, respectively. Those two are both relatively easy to do. Problem comes if you try and get an aldehyde out, because obviously if you add the acidified potassium dichromate and heat it, it adds and then it adds again, and so you get a mixture of these two. To get the aldehyde specifically, you need to change your setup. So instead of having the condenser vertical, you set it up for distillation. And so when the aldehyde is made, it boils, it changes into a vapour, it goes into the condenser, condenses and then drips out of the end, thus separating the aldehyde from the reaction mixture before it has a chance to get oxidised further to become a carboxylic acid. Okay, next up is the elimination of water from alcohols. In this process, the OH group is taken off the alcohol and one other hydrogen from an adjacent carbon. So, for instance, if I'm removing this OH group, I take off a hydrogen from an adjacent carbon, not the same carbon which is bonded to the oxygen, but one of the ones next to it. Now, if there's more than one carbon next to the carbon which is attached to the OH, it can be taken from either, and both of the products are made. Sometimes, like if I eliminated water for any of these three molecules, there's only one product. But sometimes there's more than one product, and that's the basis of a lot of questions, especially making two products or making a product that has easy isomerism, because the product of that reaction is an alkene. And I'll show you a couple of examples of elimination of water now, so you can see how it works. Okay, first off I'll use this propan-2-ol because it's here. You're going to remove the OH group, and you're going to remove a hydrogen from either of these carbons. Now they're both the same, so it doesn't matter which one I take it off of, but just check. Both of these are methyl groups attached to that carbon, and so they're both the same. But sometimes you have a methyl group and an ethyl group, for instance, and so they'd be different. I'll show you one of those next. So I've circled in red the OH group I'm going to take off, the H I'm going to take off, and that's going to leave me with a double bond between these two carbons. The one that I took the OH off of and the one that I took the H off of. So this one will give you propene and water. It's the elimination of water, so water is also made in that reaction. Now for this reaction to occur, you need the presence of an acid catalyst, often it's phosphoric acid, and you need to heat it at reflux. And those conditions often get you as many marks as drawing out the product, so learn those conditions. Next I'll show you what happens if these two groups are not the same. So what I said before, a methyl group and an ethyl group. So the process is still the same, you still take off the OH group and an adjacent hydrogen, but this time it matters whether you take off this hydrogen on the methyl group or this hydrogen on the ethyl group, because they give you two different products. And both of those things happen. And so you get two products of this reaction, and you need to be able to draw both of them and name both of them. So this was butane-2-ol. If I remove the OH and that red hydrogen, then I get but-1-ene. If I remove the OH and this H, I get but-2-ene. So if I take off the reds, then I get this top product, but-1-ene. If I take off the greens, I get the bottom product, but-2-ene. And if you've seen the alkenes video, you'll know that but-2-ene can be drawn in two different ways because there's two different stereoisomers. This one will be trans-but-2-ene. There's also cis-but-2-ene if I took off that hydrogen rather than this one. And this type of thing, butane-2-ol especially, is the basis of a lot of questions. So I'll say butane-2-ol was heated with phosphoric acid to produce a mixture of three different compounds, say A, B and C. A is a structural isomer of B and C, and B and C are stereoisomers of each other. Write out the structures of A, B and C. That's a classic question. Sometimes it's with butane-2-ol, sometimes it's with other things, but normally it's just one structural isomer and then a couple of stereoisomers, and that's difficult enough. Now the last one is substitution of a halogen. So it is possible to do an organic reaction where I just swap the OH group for a halogen. So either chlorine, bromine, iodine, those ones that tend to come up. And to do this, you just react the alcohol with an acid and halide solution. The easiest way to do that normally is just to add a hydrohalic acid, like hydrochloric acid or hydrobromic acid, and that just swaps out the OH for whatever the halogen is. You can do it with, say, sulfuric acid and sodium chloride. That will give you a chloro group instead of the OH. So I'll give you an example of that substitution reaction. They're very simple. You just take the OH off and put the halogen on. So if I take propane-2-ol and add hydrochloric acid, then I've got the acid part, I've got the chloride ion, and the chloride ion will swap with the OH ion to make 2-chloropropane and an OH minus ion. So in terms of the change in the organic molecule, it goes from being an alcohol to being a haloalkane. All you've done is swapped the chlorine with the OH. And that's all for this topic. Thanks for watching. Hope you can join me in the next one. Goodbye.